Hello, my name is Trey Jiron. I'm a senior physics student here at Colorado Mesa University, and today I'll be talking about the research I've been doing with Dr. Collins this last semester. Estimation of molecular energy via quantum circuits. Whenever anything quantum comes up, whether it be quantum information, quantum mechanics, I always like to think of this quote by Richard Fineman, a well-known physicist. I think I can safely say that nobody understands quantum mechanics. So at any point in this presentation you get lost or confused, like that doesn't quite make sense. Don't worry, you're in good company. This stuff is not very intuitive and a little bit complex, though I'll try to simplify as much as I can. That being said, here's an overview of our talk. First, we'll start with classical information, what it is, what it means, and how we use it. We'll go to quantum information, how it differs from classical, how we use it, and what it can do. We'll go into my research, estimation of ground state energies. We'll find the results of that research, and lastly, we'll conclude. So with that, classical information. What is classical information? Well, classical information is what powers all your electronic devices. Your phones, your tablets, your computers, everything you own runs on classical information. It uses a string of bits to represent information. A bit is a physical thing that it can be represented as either 0 or 1. It uses a string of these bits in order to store information. It then uses logic gates to manipulate this information in such a way that can produce everything you know. Everything from video games to computers runs on this classical information. The same principle of a bunch of string of bits and logic gates that all work together to produce everything you own electronically. So how exactly does this classical information work? Well, as I said, it uses bits, a binary language of 0 and 1. A bit can be either 0 or 1, nothing else, nothing in between. It can be 1 as in true and 0 as in false. And a computer uses a whole bunch of these bits in order to compute everything it does. A physical idea of this bit would be an electronic signal. For example, you can think of a 0-volt signal as being 0 and a 5-volt signal being 1. Then a whole bunch of these signals are sent off, and the computer receives these signals, computes them as a 0 and 1, and then manipulates this information. The bits store information, and we can use this information in various kinds of ways. For example, binary addition. In binary addition, 0 plus 0 equals 0, 0 plus 1 equals 1, and 1 plus 1 equals 0. Now that last one is a little bit confusing. However, you have to keep in mind a bit can't be 2. A bit can either be 0 or 1, nothing else. So 1 plus 1 has to equal 0. What happens is that 1 gets carried over. So, for example, 0, 1 plus 0, 1 equals 1, 0. The two 1s add together to form a 0, and that 1 gets carried over to the next spot. This is the same as 1 plus 1 equals 2. And this is the basic principle that runs everything you run on an electronic device. There's a whole bunch of zeros and ones that are all manipulated in some form or fashion by gates to form all the information that you know. However, there's a limit to this. How so? Well, there's some classical problems that grow exponentially. What do I mean by exponential growth? That's a phrase that's been thrown around a lot nowadays. The exponential growth grows very, very quickly compared to other ways. For example, the most well-known idea of exponential growth is take a chessboard, put 1 grain of rice on the first square of the chessboard, put 2 on the next, 4 on the next, and so on. By the time you reach 20th or so square of that chessboard, you will have many grains of rice as all in the entire world. Very quickly, exponential growth goes out of hand. So, for example, factorizing a number is an example of this exponential growth problem. Classically, as the number goes bigger, the number of bits, the number of steps you have to do to factorize that number goes exponentially. So you end up with this 2 to the n idea, this exponential growth. The bigger number you want to factorize, the more steps you have to do to factorize it. This, as you guess, can go very quickly out of hand. And soon, at a big enough number, it requires more power to factorize than an entire universe. So, what do we do? Well, we'd like something more like polynomial growth, as seen here. This graph down here shows the difference between exponential growth, the blue line, and polynomial growth, the red line. You can see polynomial growth allows us a much more gradual increase in the power we need in order to factorize a number, for example. So this polynomial growth is much, much better for these types of problems. And it's these types of problems that we want to see as polynomial growth. How do we achieve this polynomial growth then? Well, that's what quantum information is for. Quantum information started in the early 1980s with Richard Fineman, who first proposed the idea of using quantum mechanics to manipulate and store information. From there, developments were quickly made and procedures were very quickly developed. Various ways of creating these qubits, that I'll get into later, and manipulating information were very quickly developed. And it's now one of the hardest areas of research in physics because of all the things it can possibly do. So how does it exactly work? Well, before we go into that, we're going to talk about what is quantum information. It uses physical systems to store information, physical quantum systems, stuff like electrons and photons, things that exist on a very small scale of nature. These physical systems obey quantum mechanics, and we can use these laws to manipulate and store information. And in theory, by doing this, we can achieve that polynomial growth that we seek, which will be much more efficient than classical information. How exactly do we store these information in a quantum physical system? Well, we use something called a qubit. A qubit is akin to a classical bit. However, unlike a classical bit that can be either a 0 or 1, a qubit can be a superposition of the two. Quantum superposition is one of the things that quantum information takes advantage of. Quantum superposition states that an object can be two values or more at the same time. The most well-known example of this is Schrodinger's cat. The cat can be either alive or dead in the box, and until you open the box, you will not know if it's alive or dead. Very ironically, Schrodinger's cat came up by Schrodinger, who came up with the idea to dismiss superposition. He came up with the idea to kind of ridicule it by saying, look how ridiculous this is. This can't be true. However, nowadays it's one of the most well-known examples of quantum superposition. But regardless, this idea of quantum superposition of having two distinct states exist at the same time is what we use in quantum information. How do we use this? Well, as I said, we use a qubit. A qubit can be either 0 or 1. However, it can also be a superposition of the two. And that is visualized via this block sphere. For example, you have on a block sphere, you can visualize a qubit as being at a 0 state and the 1 state down here. However, a qubit can also lie anywhere else on that sphere. And on that sphere is a superposition of those two states. For example, down here, you have a 0 plus 1 over the square root of 2. This is a superposition of 0 and 1 that exists at the same time. Your qubit is both 0 and 1 at the same time, something a classical bit could never achieve. It should be worth noting, however, that when you measure the qubit, it can still only be one of two outcomes. Just like how when you open the box of Schrodinger's cat, it can be either alive or dead, the qubit can either be 0 or 1, or some kind of two of those two outcomes. You cannot observe the qubit in a superposition of the two states. It can only be measured in one of the two ways. How does this actually work? Well, we look at measurements. Quantum mechanics gives us the idea of how the probability of measuring that qubit will change. So qubits can be measured, and when they're measured, they can either measured in a computational basis, the 0 and 1 you see here, or in another kind of basis. However, no matter what basis it is measured in, we can reduce it to a computational basis. All that means is that we can reduce any kind of crazy basis we have to simple zeros and ones that we can compute classically. How exactly do we know what probability we'll get a 0 or 1? Well, the laws of quantum mechanics gives us. Say you have a state psi alpha 0 plus beta 1. Quantum mechanics gives us the ability to predict what the probability is we'll get a 0 and a 1, as seen here. This math down here will tell us what the probability is we'll get a 0 or 1, and we'll be able to predict which one we'll get. So this gives us the ability to predict our measurements. What do we do from there? Well, we look at how we actually build these systems. How do we actually make these qubits, and how do we manipulate them? These qubits can be made in various sorts of ways. One of the most well-known examples is take an electron. The electron has spin. It has spin up and spin down. Spin up corresponds to h bar over 2 energy, and spin down corresponds to negative h bar over 2. Take the electron, put it in an electric field, and you can imagine, depending on the strength, timing of that field, you can rotate that spin around. And that will be a superposition of both spin up and spin down until you measure it. Likewise, you'll have photons. You can polarize a photon vertically or horizontally. You can also polarize it and mix the two. These are just two examples of a kind of physical qubit system. We won't concern ourselves too much with the details. There's another way this is an IBM machine as seen here. There's a whole bunch of classical circuits, and in the middle is the superconductant. The superconductant is what actually makes the qubits. However, when we have these qubits, we want to manipulate them. And that's where quantum circuits and quantum gates come in. These quantum circuits and quantum gates manipulate the qubit. And no matter what system you have these universal gates. These universal gates allow you to state that as long as you implement the gate correctly, when you use this gate to manipulate the qubit, you'll get this outcome. These universal gates can be implemented on any kind of physical device, and as long as they're implemented correctly, you can predict the outcome of that. So, these universal gates are very important. How do we actually represent them? These quantum gates can be represented mathematically as matrices. For example, a poly X gate is represented by a matrix 0, 1, 1, 0. This is akin to a classical NOT gate. A NOT gate turns a 0 bit to a 1 bit and a 1 bit to a 0 bit. Likewise, a poly X gate is the exact same thing but for a qubit. Seen down here, the sigma X is a poly X gate operates on state 0. It flips that 0 qubit to a 1, and likewise, if you operate on a 1 qubit, it will flip it to a 0. It is the exact same thing as a classical NOT gate. So we have this procedure then that states, well, as long as you can implement this gate correctly, when it acts on the qubit, you'll get this outcome. So, where do we go from here? Well, we string a whole bunch of these gates together to form a quantum circuit. This is what a quantum circuit looks like. This is a project I worked on a few years ago. I'll explain more about what this all exactly means later on. But for now, you have to keep in mind, these quantum gates operate on different qubits, and can allow and operate on different qubits at the same time. For example, this circuit has 1, 2, 3, 4, 5 qubits operating on it. Each line corresponds to a qubit, and this bottommost line corresponds to the classical measurement of that qubit. That bottom line corresponds to when we actually observe the qubit, what do we get? So we have a whole bunch of qubits, and these qubits can actually interact with each other. How do we do this? Well, there's a specific gate for this called the C-NOT gate. The C-NOT gate is akin to a XOR gate in classical logic, where the state of one bit affects the state of the other one. For example, if the state of the X, the topmost qubit, is 0, then the bottom qubit will stay the same. However, if the topmost qubit is 1, then it will flip, it will not the bottom one. For example, 1, 0 flips to 1, 1, and 1, 1 flips to 1, 0. It flips that bottommost qubit if the top one is 1. This is akin to the XOR gate over here, which does basic addition. And what this allows us to do, the C-NOT gate allows us to entangle two qubits. The state of one qubit affects the state of the other. How exactly does this work? Well, I have an example shown here. The measurement of one qubit affects the measurement of the other. And how this works is that we use the C-NOT gate. So, for example, at size 0, we have a state of 2 qubits. Each qubit starts in the state 0. So we have a state 0, 0. We then operate a hammer-on gate on the top qubit, qubit 1. This is a transformation that creates superpositions. Once again, this is a rotational like block sphere that creates a superposition of zeros and ones for that qubit. So all of a sudden, we now have a superposition. Our state psi 1 is now this 1 over square root of 2, 0, 0, plus 1, 0. Lastly, we do a C-NOT gate. Once again, this will check the topmost gate and check, and then say if it affects the bottom one. However, once again, it's a superposition of 2. So, your psi 2 state, the final output, is then 1 over square root of 2, 0, 0, plus 1, 1. These two states are now entangled with one another. The state of one affects the state of the other. And this is one of the things that quantum information is able to take advantage of. So, we have quantum entanglement or quantum superposition. What do we actually do with this? Well, there's a lot of applications for quantum mechanics, or quantum information rather. For example, cryptography. Quantum cryptography is a field that is interested many, including the military, because in theory it allows you to tell when someone's eavesdropping on you. When you observe a quantum system, you change that system. Observation equals change. So, in theory, if you send information, and the information you get back is not the same as you received, you know that somewhere in between, someone had to observe it. Someone observed that information and changed it. You know there's an eavesdropper. It's not quite that simple, but that's the basic principle of the matter. There's also some other uses. Quantum search algorithms and quantum factorization algorithms. systems. Both of these have the ability to do what they need to do faster than classical machines. And this is the idea of quantum supremacy, the idea that a quantum computer can do something faster than a classical computer. Now, this idea of quantum supremacy has existed since the early 1990s, theoretically. It's only until very recently, last year, that Google proposed the idea that they have finally proven it. They've proven that the quantum machine could do something faster than a classical machine. This sparked a lot of controversy. I'm not well versed in the exact details of it, however, it may not be as clear-cut as Google may have wanted it to be. But, regardless, it does show that we are at the very least rapidly approaching this idea of quantum supremacy. So, what else can quantum computers do? Well, they can simulate stuff. Quantum computers can be used to simulate systems, including other quantum systems. After all, what's better simulating a quantum system than a quantum system? And when we do this quantum simulation, we can possibly achieve that polynomial growth. Where other classical ways may have the exponential growth, we can get polynomial, and this will allow us to trace information untraceable by classical systems. It should be worth noting, however, this does introduce an error. Remember, all measurements are probabilistic. We have a chance of getting 0 or a chance of getting 1. We cannot say for certain which one we'll get. That means sometimes you will not get the answer you suspect, because it says probability. Now you can manipulate the probability to give you the right answer most of the time. However, you can't do it all the time. This probabilistic answer is something that people who are looking at quantum computing is all considering. However, regardless, we are looking at quantum simulation, and that brings us to our research. Estimation of ground state energies. Now, the ground state energy of a molecule is the lowest possible energy of that molecule. And it turns out that for anything more complicated than the hydrogen atom, it's impossible to find the exact ground state energy. The hydrogen atom is the only thing that we can find the exact mathematical ground state energy for. Anything more complicated than that, we have to compute numerically. Why is that? Well, let's look at the Hamiltonian for the hydrogen molecule, the next step up from the hydrogen atom. The Hamiltonian is the kinetic energy T plus the potential energy V. When you plug everything in, this is what you get. A whole bunch of terms that interact with one another. It's a mess. So, it turns out that you can't directly compute the ground state energy from this. We have to estimate it. How do we estimate the ground state energy? We turn to an idea called the variational method. The variational method gives a numerical way to find the ground state energy. How does it do so? Well, it finds the upper bound of that ground state energy via this equation here. We take that Hamiltonian, that big mass before, and we act on it by a state that we choose. When we act on the state on the Hamiltonian, we'll get a number. That number will be the upper bound of that ground state energy. That will tell us that our ground state energy cannot be larger than that upper bound. What we then do is that we choose a different state. If that state gives a bigger number or a smaller number. And we want to walk our way backwards. Walk our way down until we find that minimum upper bound. Once we find that minimum upper bound, we can say with certainty that is our best estimate for the ground state energy. So, how do we implement this idea on a quantum computer? Well, we need to represent our Hamiltonian, H, and our state, psi, theta, as a bunch of as qubits and gates that we can implement on a quantum computer. Now, for this research, we use a state psi theta equals e to the negative I theta x0 y1, 0, 1, where theta is a parameter that we choose that we'll walk with to walk our way backwards to that minimum. X0 is a poly x gate working on the 0th qubit, and y1 is a poly 1 qubit, poly 1 gate acting on the first qubit, and 0, 1 is the beginning state. We use this state added on the Hamiltonian. Now we have our state as a bunch of system of gates. Now we represent a Hamiltonian. How do we do that? Well, we use some papers that look at the same thing. Some papers use the Breivik-Kitov transformation, while others use the Jordan-Wigner transformation. But in either case, the procedure is the same. You start with a real space molecular Hamiltonian, that big mess I showed you earlier. You take the Born-Oppenheimer approximation. This pretty much states that we'll ignore any movement of the nuclei. We compute over the Hartree-Fock states and write in second quantized basis. Down here is the second quantized basis. For the second quantum, the A and A dagger terms are very similar to the creation annihilation operators you may be familiar with, while the H's are integrals over space. The exact transformation isn't too important. What is important is that once we have the second quantized form, we can then take a Brave-Kirchhoff transformation. And this will transform our Hamiltonian into a system of gates and qubits that we can operate on. Once we have that, we apply our parameter onto the Hamiltonian, find the expectation values for the Hamiltonian, and compute new parameters. And we repeat this process, working our way backwards to find that minimum. That minimum expectation value, that minimum Hamiltonian, will then give us the best estimate of a ground state energy for that molecule. So, this is where our research begins. What we want to do is we want to implement this method on an IBM machine, using other papers as a guideline. So we're using a paper that looks at the ground state energy of a hydrogen molecule. What we want to see is, can we replicate the results that they got on an IBM machine? IBM offers a quantum computer that is accessible to the public. You do have to request access, I believe, but it is accessible to the public. And if we can implement the same method and get similar results on this machine, then we know this method works on the IBM machine, and we can use the same method on different molecules and get new results. So that is the goal of our research right now. See if we can replicate results on this IBM machine. So, what we look at is what the paper did for the gates of the Hamiltonian. We start with a series of gates for the hydrogen molecule. And what we get is something seen here. This is our Hamiltonian that we can implement on the quantum computer. These G's are constants I'll get into later, and these Z's, Y's, and X's are expectation values. These expectation values that we can measure. This is the picture that's from the paper I'm talking about. This gray box right here is the actual parameter. This is the e to the negative I theta x0 y1 0 1. This is the parameter, and down here the z theta is where we input that theta, our parameter, and we change that theta, we walk our way backwards to that minimum. We have this parameter applied on the quantum computer, and now we have applied, we can now find out our Hamiltonian. How do we do that? Well, before we get into that and the results, I want to address any possible issues we may have with this. Well, the papers we're looking at may have different physical systems than what we're looking at. For example, some papers use a trapped ion quantum computer. The IBM machine is believed to be superconducting. Now what this means is that some gates are not directly transferable. Some gates on a trapped ion computer may not be directly transferable to a superconducting computer. Now we can translate them. Universal gates allow us to build any other kind of gate we want with them. It just takes more effort, and we have to make sure that we are accurate in our translation. Furthermore, we have to make sure that our measurements in different bases are correct. What do I mean by different bases? Well, if we go back, these z, y, and x's, these all correspond to a specific basis. Whenever our block sphere, we have the z-axis, the y-axis, and the y-axis. What we want to do is that we want to measure along each one of those axes, and that's our basis. So, if we want to measure along the z-axis, that's fine. That's the default axis we measure upon. We don't make any changes. However, if we want to measure upon the y and x-axis, we have to rotate our system. And that rotation allows us to measure any different bases and get the values we need. So we have to make sure our rotations are correct in order to get the correct expectation values. So, the possible issues addressed. What are the results? Well, we look at building the circuit on the IBM machine. IBM's Q experience allows for a very intuitive circuit designer that allows you to click and drag gates onto the circuit. However, while very intuitive, this is a little bit simple, and in future we'll most likely have to use Qiskit. Qiskit is a Python package that allows us to make more complicated circuits and automate the system, allowing us to do more results much more quickly. But for now, this simple click and drag intuitive method is more than enough. I'll just take a bit to explain what exactly all this is. So, this is what IBM machine looks at. It has two qubits, Q0 and Q1. They both start on the state 0. Then, the Q0 hits an identity matrix. The identity operator just tells it to stand by, keep the same, don't worry. Then the Q1 hits a poly X gate. Remember, this is the NOT gate. It flips a 0 to a 1. So now we have a 0, 1. The next set of gates are all Y and all X's. These are rotation gates. Remember that block sphere. An all Y will tell the qubit rotate along the certain angle along the Y-axis. while all x will tell it to rotate at an angle along the x-axis. These will just rotate that qubit along that block sphere to create a superposition of zeros and ones. They then get a C0 gate, which I talked about earlier. The two states are now entangled. Q1 gets an all x gate, once again rotation along the x-axis by a specific angle. Another C0, then some more rotations. Lastly, these are the measurements. They are measured along the z basis. Now down here, worth noting is the classical measurement. Now this does not mean that this qubit is 1, this qubit is 0. This is just notation. This is just saying this is the measurement for qubit 0. This is the measurement for qubit 1. It has nothing to do with the actual measurement of the qubit. This is just a notation thing. So the IBM machine gets a series of gates and it operates on the qubit in a physical way according to these gates. I do not know the details of how they implement these gates, but they're able to do so. And with these gates, what we then do, once we have all these results, how do we actually get what we want? Well, we want to find an expectation value for a specific qubit on a specific basis. How do we get the expectation value? There's two main ways. One is via measurements. The actual measurements themselves will give us probabilities. In the IBM machine, they'll give us probabilities that we can then do a specific way. We can take the probability again 0, times by 1, then take the probability again 1, times by -1, and we add those two together, and that's our expectation value for the 0th qubit along the z basis. For example, we also do this mathematically as seen here. We have to take our state and operate on this state here. The exact mathematics isn't too important, but what is important is realizing that we are able to use this mathematical formula to check the IBM results. We use this to check this. The mathematic can check the measurements, and if they two all match or are close, we can say, okay, the IBM machine is doing what we suspect it to do. We're good to go ahead. Now, for this system, we're going to be using theta equals pi over 3. It's a non-trivial theta that gives us some interesting states by still being fairly easy to calculate. So, what do we get? For our z measurements, this is what we get. This is what the IBM machine spits out. It gives us probabilities. And using these probabilities, we can get the expectation values. Once again, we use the same procedure. We state that 0, 0, 0, and 1, 1, all those states correspond to a multiplier of 1. So we'll multiply the probability again in any of these states by 1. On the other hand, 1, 0, 1, and 1, 0, the probability again in these states will multiply by -1. And then we'll add those together to get the expectation value. For example, the 0th qubit, which is the rightmost number here, has about 75% chance of getting 1, and 25% chance of getting 0. We'll multiply -1, we'll multiply 75% by -1, and we'll multiply 25% by 1. We'll add those together and we'll get about -50% or -0.506. We'll do the same for the first qubit, the leftmost number. We have about 75% chance of getting 0, multiply that by 1, a 25% chance of getting 1, multiply that by -1, add those together, get 0.503, as seen here. If we want to know the probability of getting both, we look at this, 0, 1, 1, 0. Both of those have a multiplier of -1. So when you add them together, it's going to end up being 1 times -1, -1. And then repeat this process for all other bases. It's worth noting that look at these two spots right here. These gates are different from the gates before. These are the rotation gates I was talking about, that rotation of the block sphere that will change our basis measurements. These what these two extra gates do. They rotate so we can change our measurement basis. And upon doing so, we get different results as seen here. We repeat the procedure as before. We take this, times it by 1, take these two, times it by -1, take this one, and times it by 1. We add those all together, and we get expectation value for our y basis. We repeat the process for the x basis. Once again, note these two gates rotate our system in such a way that we can now measure along the x basis. We repeat the procedure, times this by 1, times these two by -1, and times this by 1, and together. And now we have expectation values for all our bases. What do we do with them? Well, we put them in this equation right here. These G0s, G1s, and so on are constants. They depend on the bond length of the hydrogen atom. They've come out of some quantum chemistry stuff that we don't quite understand right now. However, we do have a table, and this table will tell us what these G's are for a given bond length. So we can solve this table, and we see what we have for an R equals 0.75 angstroms, and for theta equals pi over 3. We plug in the G's, we plug in the expectation values we found from IBM, and what we get is we get a expectation value of the Hamiltonian of negative 0.11 hat trees. A hat tree is about equal to 27.2 EVs, or 4.3 times 10 to the negative 18 joules. So a very small number. Now, what we suspect to get is somewhere along the lines of negative 0.25. These are very close to each other. I'll talk about the discrepancies between the two in the conclusion. However, what this states is that we know for a fact that the ground state energy of the hydrogen molecule for this bond length cannot be greater than negative 0.11 hat trees. It has to be less than. And this is our result. So, to conclude, what we have shown here today is we have shown that it's possible to simulate previous results using this IBM machine. Now, there is some small error. There is some error in the actual measurements themselves. Now, it should be worth noting that the IBM machine has two modes. It has a simulator mode and has a physical system mode. Simulator will just simulate the physical system. However, the physical system you have to require access to, you have to wait in a queue, and you only get to access it certain times a day. So I use the simulator. The simulator, however, does simulate error. As I said, you have those probabilistic errors. You also have the fact that the gates themselves are not perfect. The gates are not perfect as they are mathematically. There's small errors in the gates themselves. So these kind of small errors spring up, and that can help explain the difference in these two numbers. However, regardless, what we like to do in future work is we like to reproduce the same results with different values of theta and R. We're going to produce something like this figured down here. This is a heat map of the Hamiltonian versus a theta, and an R. What we did today was we reproduced one part of this map. What we'd like to do is at the very least we replicate a good portion of this. If we can replicate a good portion of this and all results are comparable to this, then we can say, okay, this method works on an IBM machine. This method works on an IBM machine, so we are able to use the same method on different molecules. Once we use the same method on different molecules, we can then get new results. So that's what a future work looks like. So, to conclude, we started with the explanation of classical versus quantum information. We showed how we can use quantum mechanics to simulate physical phenomena. We used these quantum systems to simulate other quantum systems. We used other papers as guidelines to see if we can get expected results. Use these papers to see what they got. You implement the same method on the IBM machine, see if it's to compare. And if they compare well enough, often enough, then we can use the same method on different molecules in the future. These molecules will allow us to get new results, more interesting data. So there's something that I want you to take away from this talk, everything else, just remember this. The idea is we can take quantum mechanics, the laws that dictate the smallest things in the universe, these abstract laws that usually have no idea how to be ever useful. We're able to take those same laws and apply them in such a way that we can learn new things about our universe. And that's what I want you to take away from this talk. These are my references. Any questions?